with the section on NMR spectroscopy. So hopefully in the next half an hour to 45 minutes or so, you're going to get a brief introduction to what NMR spectroscopy is. And basically, it is a tool that organic chemists and biochemists use in order to determine the structures of organic compounds. So why would you need to determine the structure of an organic compound? Right, so generally what happens that you are going to, in the course of your careers or in your time as students, you're going to make certain compounds. And when you make certain compounds, you might want to know if I did make it. You know, did I set out to make what I made? If you're going to bake a cake, you wait to taste the first piece of cake, and if the cake tastes sour, you know that it's not generally a cake. Maybe you made something else. If the cake tastes nice and sweet and it's sugary, it might be, and it has a nice texture, you say, okay, I did make my cake. In the field of organic chemistry, we need to prove that a particular structure is what I said I'm going to set out to make. Now imagine if you found the cure for the coronavirus and you were getting a structure of a compound and you didn't know whether that structure was correct or not. Nobody would actually take that cure. So we need to prove to people that when we do sell them a drug or we do sell them a compound, it is exactly what it is we say. So we're going to use NMR spectroscopy in order to do that. In other fields like natural products chemistry and in some fields of biochemistry, we isolate organic compounds. So we take a living organism, we can isolate a compound from a living organism, and we can then subject it to NMR spectroscopy and see what organic molecule is formed by that living organism, be it plants or be it humans. We can actually determine the structure of that particular compound. So it's a very, very important tool. It's a very, very nice tool to have because we can unequivocally say, and by unequivocally I mean without a doubt, say that this is the structure of that particular molecule, right? So that's why we need NMR spectroscopy, and you'll see by the time you finish this course, you'll be able to take an NMR spectrum and work out a structure of a simple molecule, right? So at second year level, we just deal with simple molecules, and as you get higher and higher in the years, my master's and PhD students work out molecules with 30 carbons, 20 carbons, 40 carbons at times. So the big macromolecules can also be worked out using NMR spectroscopy. So at an introductory level, what is NMR spectroscopy and how does it work? So generally it works with the concept of particles spinning, right? We know from our physics in first year that electrons that are charged are spinning particles. And these electrons that spin, much like how the Earth spins around its axis and then has a particular orbit around the sun, electrons also spin, and when they spin, they create a magnetic field. And that magnetic field has consequences in many different fields. So we use the charged spinning particles of electrons in varied fields in science. And you can read up about that. You're probably familiar with some from your first year. The charged particles that spin have two allowed spin states. So electrons that spin have two allowed spin states. We denote it as plus half and minus half. And these are spin quantum states or quantum spin states. Generally, what it means by a plus half and a minus half is that a particle can spin in one direction, so maybe from right to left, and then it can also spin in the other direction, maybe from left to right. If I want to visualize this, if I'm dancing with a dance partner and I spin them or twirl them one way, I'm spinning them one way, that's the plus half, and then if I spin them the other way, that's the minus half, right? So there's two allowed spin states in these electrons, which are charged spinning particles. But NMR spectroscopy doesn't make use of electrons. I'm going to make that very clear. We don't consider electrons, well, we do consider them to some effect, but they are not responsible for the resonance, right? The resonance is going to be responsible, or the resonance that you're going to see is going to arise from these nuclei. And those are protons, the proton nuclei, right? 1H, carbon-13 nuclei, nitrogen-15 nuclei, fluorine-19 nuclei, and phosphorus-31 nuclei. And generally what these nuclei do, and you'll notice that I only have a few here, because not all nuclei are NMR active, right? Only certain nuclei are NMR active, and these nuclei have the properties of having two allowed quantum spin states. So just like electrons, these nuclei here also have a spin quantum number of +½ and -½ right? So if you think back to first year, your nucleus or your atom is made up of a nucleus, and in that nucleus you have protons and neutrons, right? So if I have a mass number of 1 in hydrogen here, which means I only have 1 proton and 1 electron in my hydrogen atom. I don't have any neutrons here. If I have carbon-13, it means that I have 6 protons and 7 neutrons in this nucleus. And I also have 13 electrons, or 12 or so electrons going around, in the molecule. So the nucleus consists of protons and neutrons, and that contributes to the mass number. And you learned that in first year. And you notice that there's one thing in common with all these nuclei that are NMR active. They all have odd mass numbers, which means they either have an odd number of protons or odd number of neutrons. And these are NMR active nuclei, which means that they spin in one direction and they can spin in the other direction, right? So they can spin in 2 directions, and that's what gives them the properties, to be used in NMR spectroscopy. All right, so let's spend a little bit of time on this particular diagram that I've put here to show you what happens to this nucleus. And I'm going to forget about the carbon, fluorine, phosphorus, nitrogen nuclei, and I'm just going to concentrate on protons. Remember that when NMR first started, was started for using protons with just 1 proton in the hydrogen atom, and what we can have is a situation, and each of these, I've drawn these balls here, represent the hydrogen atom with 1 proton in it. And the arrow shows you the direction in which they spin. Now, what do we mean by the arrow shows you the direction in which they spin? So if I spin now, if you look at this particular hydrogen atom here, if this is spinning from left to right, we can say that it's creating a magnetic field where this is the south pole and this is the north pole. So the direction of the magnetic field is from south to north. And the arrow shows the direction from south to north. And that's why we say that the magnetic field is in this direction, right? As opposed to this particular direction. Here we can see now that this is south and the arrow is showing me where is north, right? So you can see that this particular hydrogen atom is different to this particular atom in that they're both spinning in opposite directions, right? So if I look at that and that, they're both spinning in opposite directions. I can also orientate it randomly to spin in this particular direction where this is now south and that's north. And you can see these are all angular. So all the spinning, that we're seeing with these atoms is all angular. It's not straight down. Right? So these nuclei can spin in random orientations, right? So if you take a soccer ball in your hand and you can spin it any which way you want, right? You can spin your soccer ball left to right, right to left in various ways, tilt it one side and spin it, tilt it the other side and spin it. And that's what happens, to these protons, to these hydrogens with 1 proton, so I'm generally going to call them protons. And that's what happens, they spin in all directions, right? And, generally, as I said, they can spin to the right and to the left. They have 2 spin states. Then I'm going to take all these electrons, right? So this is a sample sitting on the bench in your laboratory, and this is how the nuclei behave. I'm going to take it to the NMR spectrometer that we have in chemistry. In chemistry, we have 2 NMR spectrometers. And I'm going to put the sample into the magnet, right? And this is now an external magnet that we have. So the NMR spectrometer is a very expensive piece of equipment. It's got an external magnet, and that's called the applied magnetic field. So remember I said that each of these spin and they act like small magnets. So these are micromagnets. If you can imagine a nucleus of a proton as a micromagnet, right? A very, very tiny magnet that you can't see, but they spin and they have a south pole and a north pole, just like a bar. So if you, I don't know if you played with a bar magnet anytime, right? But in your bar magnet, you have a south pole and a north pole. If you take the two magnets and put them together, they can either stick together or sometimes they'll be pushing apart. If you bring the two terminals, like two norths together, they'll go apart. You know, if you bring the north and the south together, they'll probably stick together. So these are like micromagnets in your sample. And when you put them in an applied magnetic field in a bigger magnet, these spin states, these spinning is not random orientated anymore. They now take on two spin states. So they either spin in the direction of the applied magnetic field. So if your big magnet says from south to north, like this arrow here, right, which means, for instance sake, I'm just saying if it spins from the left to the right, so if your magnetic field is spinning from left to right, you know, we create a south to north magnetic field or applied magnetic field. The alpha spin state spins in the same direction that creates that south to north magnetic field, right? And we say then that the proton aligns with the field or with the applied magnetic field, right? So if we take this, we put it here, the protons can either be aligned with the magnetic field or opposite to the magnetic field, right? So how can you visualize this is look at a river. A river flows one way, right? And when the river flows one way and you throw something into the river, right, that is going to flow in the direction of the river, right? Going into the sea maybe, right? So whatever you put in there, it flows in the direction of the river, and it does flow in the direction of the river because that will require the least amount of energy. If you now want to say you're going to dive in and you're going to swim against the river because you want to get out on the other end, you're going to have to apply energy now to swim against this river, right? And that's your beta spin state. So to spin in the other direction is very, very difficult to do because you need energy in order to spin in the other direction. That's going to make you swim against the river or, you know, go against the applied magnetic field. So obviously you can see that this beta spin state is higher in energy than the alpha spin state. We don't require much energy here. This is the more relaxed alpha spin state, lower energy spin state. And this beta spin state opposing the applied magnetic field or opposite in direction to the applied magnetic field indicates that this is a high energy state. More energy is required here. All right, so just to recap, that spinning charged particles create a magnetic field, and you saw that here. And when you put it into an applied magnetic field, they either align themselves with the applied magnetic field or against the magnetic field. But most of the nuclei, and I say most of the nuclei because they're just a few that align themselves against the magnetic field, right? Because they are higher in energy. But that's a very, very few protons do that. Right? Those who are charged enough can actually spin in the other direction, but most spin in the direction that allows them to be aligned with the applied magnetic field. Now, let's take it one step further. If we subject the sample to a pulse of radiation, so what I'm actually doing now is I'm giving the sample energy. Remember I said in order to swim against a river, you need energy to go the other way. So if you want to, you know, spin one way where the applied magnetic field is, it's fine. But if you say, no, I don't like to spin from right to left, I want to spin from left to right, you need energy. So we can supply that energy, right, by subjecting the sample to a pulse of radiation, which is equal to the change in energy from the alpha to the beta spin states. So I already mean this energy here, right? So that's the energy of your alpha state. That's the energy of the beta state. And if you're in the alpha state and you want to spin the other way, you can't do that because you don't have energy yet. So we're going to send a pulse of radio frequency radiation such that you have enough energy to say, let me stop spinning in from left to right. I can now spin from right to left because I want to spin in the other direction, not being aligned with the magnetic field. And you're allowed to do so, right? You're allowed to do so because the nuclei that we're dealing with have two spin states. I can either spin in one direction plus half or the other direction minus a half. And can you see here, I'm not randomly orientated anymore. I'm just either with or against, right? So when you're put into applied magnetic field, it's either with the spin state or against the spin state. So we can supply this energy in order for the alpha spin state to go to the beta spin state. And when we do that, we say that the alpha spin states can be flipped. And generally you see people talking about flipping the spin. So we can flip the spin from the alpha spin state to the beta spin state. And generally what that is if I'm dancing with a dancer and I'm spinning them around one direction, I'll continue to spin them in one direction until I get that burst of energy that gives me enough energy to now spin them to stop spinning in one direction and to spin them in the other direction, right? So generally that's what we do. We can flip the spin from the alpha state to the beta state, but very, very importantly, we need that energy in order to flip the spin from the alpha to the beta state. And that energy difference is delta E that I showed you in the diagram. That energy I'm talking about is radio frequency energy, right? So it's a pulse of radiation in the radio frequency range of the electromagnetic spectrum. And we call that RF radiation. All right, so that RF radiation supplies the energy to go from one spin state to the other spin state, right? To spin in one direction to the other direction. Now remember that in order to keep on spinning in the beta state, you need that energy all the time. And you probably won't get that energy all the time. So what happens when you do get that RF radiation, it slowly decays back to the alpha spin state. So you go from the high spin state, we get the energy, we go to the high spin state, and then we slowly lose the energy, and then we come back down, and then we have to spin in the direction everyone's spinning with. So imagine now that there's a march, and everybody is marching in one direction, and everybody's spinning in one direction in that march, and you are placed in that march. You're going to want to spin in the same direction as everybody else and move in the same direction as well. If you want to do go the other direction, you're going to have to get some energy now to fight off why everyone's spinning in one direction and to spin in the other direction and go the other way, right? So it's like pushing your way through a crowd, right? So you're going to need energy to do that. After a while, you might just give up and say, then just go with the crowd wherever they're going, let them take me, right? So you're going to go from the alpha spin state to the beta spin state, and as your energy drops, you're going to go back to the alpha spin state, right? So there's an energy gap here. This energy gap is very important because that hinges on how the signal comes about. So when the protons relax from the beta spin state and return to the alpha spin state, we call this flipping the spin, right? And we can flip back and forth. I can go from the alpha state, get some energy, go to the beta state, lose the energy, go back to the alpha state, get energy, go to the beta state. And we call that flipping back and forth between the alpha and beta states resonance, right? So we're resonating between the two states, the alpha state and the beta state. And hence this topic is called nuclear because we're dealing with a nucleus, right? In this case, we're dealing with a proton nucleus or hydrogen nucleus. Magnetic because they create a magnetic field. And I showed you that charged spinning particles can create a magnetic field. And resonance is because they flip between the alpha and beta states, right? So generally we call it NMR, right? And when people say NMR, sometimes people don't know what NMR means. The nuclear magnetic resonance, you can actually explain to them what nuclear magnetic resonance is by telling them about the alpha and beta spin states and the energy involved between going back and forth between the states. And you can also tell them that the radio frequency pulse that you're going to provide allows a proton to go from the alpha spin state to the beta spin state. All right. Now, as this proton relaxes from that alpha state to the beta state, All right, sorry, this is a bit of a typo. It should be as the proton relaxes from the beta state to the alpha state. All right, so there's a typo here. So as the proton is excited to the beta state and relaxes to the alpha state, they produce the signal that you see. And this is a bad drawing of mine. You can see a much better drawing in your textbook or on the internet or in other textbooks. So this is my drawing. This is a representation of, you know, an FID. It's called a free induction decay. So FID means free induction decay. And what happens is I'm showing you how the proton loses energy over time, right? So you can see this proton losing energy over time. And as it loses energy, it goes back to the alpha state, right? So all this energy is needed for it to spin in the beta state. As it loses the energy, then it goes back and drops into the alpha state, right? So that is how we get an FID signal in the NMR spectroscopy, right? Now, a computer in the instrument collects this data, and this is generally data that we collect, which is intensity versus time data, right? So the intensity of the energy of the signal over time, what happens to it. And that computer converts that intensity versus time data into intensity versus frequency data. And it does that using a mathematical operation known as a Fourier transform. Right, so the Fourier transform takes the signal here and then converts that to intensity versus frequency. So it tells me exactly what the frequency is, and that frequency is related, as you can see, to the energy, and that produces a signal in the NMR spectrum. So that long-winded story that I just told you just means that that's how I get a particular signal in the NMR spectrum. This arises from a proton that's excited to the beta state, relaxes to the alpha state. I get the data in terms of the free induction decay, which tells me how the energy changes over time. I convert that to a frequency in hertz, right? And that's how I get a signal. I plot it as a function of intensity on this particular NMR spectrum, and that's how I get a particular signal on an NMR spectrum. So this is a spectrum that you're probably going to see. It's a very simplified picture of a spectrum where I just have one resonance here, just to show you what happens when I do now picture this proton. So we plot in ppm, right? And I'll tell you why ppm just now. So in ppm of the operating frequency of the NMR. So the operating frequency of the NMR might be maybe 500 megahertz, right? But we don't need so much of energy to convert it from the alpha state to the beta state, and you know the energy won't decay. So we just need, relative to the strength of the magnet, we need a small amount of energy. And generally we need parts per million of that operating frequency. So we're looking at stuff in hertz, right? So 1 ppm of a 500 megahertz instrument will be 50 ppm, right? So the 1 ppm, sorry, that will be 500 hertz. So 500 megahertz instrument is 500 million hertz, and I'm taking 1 ppm of 500 million hertz, so that's 500 hertz between 0 and 1. So can you see, relative to the strength of the big magnet, the energy that's needed is not so much, right? And that's why we put this frequency range here in ppm, right? So more powerful magnets will have a greater applied magnetic field, right? And if they have a greater applied magnetic field, they'll have a larger operating frequency. So bigger and bigger magnets, you'll get a 500 megahertz instrument, you get a 600 megahertz instrument. Westport, we have a 400 and a 600. You also get, if you look at some pharmaceutical companies, research institutions, they have 700 and 900 megahertz instruments. So they have very, very powerful magnets in those NMRs. But regardless of how big the magnet is and how powerful the magnet is, this resonance is going to be the same, right? Because the more, or the bigger the magnet, we're not going to see a change in the amount of energy. So relative energy that's needed. So if the magnet is bigger, you're going to need more energy to flip the spin. So if I have a 300 megahertz or 3 million megahertz instrument, right, 300 megahertz instrument, I'll need 300 hertz for 1 ppm. I'll need probably the same relative amount of energy. So if I increase the magnet, I'll need more energy in order to flip the spin. So as you increase the energy of the magnet, you'll need more energy to flip the spin of a particular nucleus to go from the alpha state to the beta state. So this value will stay the same, whether it's a 300 megahertz instrument, whether it's a 500 megahertz instrument, whether it's a 900 megahertz instrument, this value is going to stay the same because the amount of energy needed to flip the spin from the alpha state to the beta state is proportional to the applied magnetic field, B naught, right? And there's an equation in your book. You can see that the operating frequency of the instrument depends on the gyromagnetic ratio of the nucleus being studied, divided by 2 pi and multiplied by the strength of the magnet or the applied magnetic field B naught. Right, don't worry so much about that equation. We're not going to use it too much in this course, but to read up about it, it shows you how that, you know, we can get to a 300 megahertz instrument and a 500 megahertz instrument and how it depends on a particular nucleus. If I put a carbon-13 nucleus in this energy that I need to flip the spin changes in this 300 megahertz instruments to 75, right? A quarter of this. That's because the gyromagnetic ratio is a quarter of the proton. So the carbon-13 gyromagnetic ratio is a quarter of that of a proton. All right, so as I said, we're not going to go too much into that, but just to let you know that that is how a signal comes about in the NMR spectroscopy. So to just recap, we go from the alpha state to the beta state and measure that energy, and that energy that we ultimately measure as a function of frequency is plotted in this NMR spectrum that you see here.